Today we shall study about continuous charge distribution in electrostatics. As shown in figure, the linear charge density lambda of a wire is defined by lambda barabar delta Q by delta L, where delta L is a small line element of wire on the macroscopic scale that includes a large number of microscopic charge constituents, and delta Q is the charge content in that element. The unit for lambda are coulomb per meter in SI unit. Now the surface charge density sigma barabar delta Q by delta S. Delta S is area element, delta Q charge content, unit coulomb per meter square in SI unit. Volume charge density rho barabar delta Q by delta V. Delta Q barabar charge content, delta V barabar volume element, unit coulomb per meter cube. All are at macroscopic level, but the element and charge constant at microscopic level. Now we consider volume element delta V barabar rho delta V. So electric field due to charge rho del V is given by Coulomb's law. Del E barabar 1 by 4 pi epsilon naught flow rho del V bata r dash square, unit vector r dash, where r dash is the distance between charge element and P, where r is a unit vector in the direction from the charge element to P. By superposition principle, the total electric field due to the charge distribution is obtained by summing over electric fields due to different volume element. E barabar 1 by 4 pi epsilon naught, E all summation all delta V. Rho delta V by r dash square r dash. By applying Coulomb's law and superposition principle, electric field can be determined for any charge distribution, discrete or continuous, or part discrete and part continuous. Now we look that measurement is done on macroscopic level, but the contents and constituents are at macroscopic level. We ignore the discrete molecular constitutions. Now, Gauss law. As shown in the figure, a spherical surface area S is taken. The radius is R. The charge is at center. Charge Q is at center. O. Delta S is a small element of area and E is the electric field. For sample application of electric flux, we consider the total flux through a sphere of a radius R which encloses a point charge Q at its center. Divide the sphere into a small area elements as shown in figure 1. The flux through an area element delta S is delta pi barabar E dot delta S barabar Q bata 4 pi epsilon naught R square, unit vector R into delta S, where we use Coulomb's law for the electric field due to a single charge Q. The unit vector R is along the radius vector from the center to the area element. Now, since the normal to a sphere at every point is along the radius vector, at that point the area element delta S and R have the same direction. So, delta pi over q bata 4 pi epsilon naught R square delta S, since the magnitude of the unit vector is 1, the total flux through the sphere is obtained by adding up flux through all the different area elements. Now, the phi barabar summation all delta S q bata 4 pi epsilon naught R square delta S. Figure 1, calculation of the flux of uniform electric field through the surface of a cylinder. Since each area element of the sphere is at the same distance r from the charge, so phi barabar 4 q bata 4 pi epsilon naught R square summation all delta S or q bata 4 pi epsilon naught R square into S. Now, the total area of the sphere equal 4 pi R square, thus phi barabar q bata 4 pi epsilon naught R square guna 4 pi R square barabar q bata epsilon naught. Equation 1 is a sample illustration of a general result of electrostatics called Gauss law. We state Gauss law without proof. Electric flux through a closed surface S barabar q bata epsilon naught. Q barabar total charge enclosed by S. The law implies that the total electric flux through a closed surface is zero if no charge is enclosed by the surface. Some important points regarding the law. Gauss law is true for any closed surface, no matter what its shape or size. No matter what its shape and size. Gauss law is true for any closed surface, no matter what is shape or size. Second, the term Q on the right side of Gauss law includes the sum of all the charges enclosed by the surface. The charges may be located anywhere inside the surface. Third, in the situation when the surface is so chosen that there are some charges inside and some outside, the electric field is due to all the charges, both inside and outside S. The term Q on the right side of Gauss law represents only the total charge inside S. The surface that we choose for the application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field, due to the system of discrete charges, is not well defined at the location of any charge. However, the Gaussian surface can pass through a continuous charge distribution. Gauss law is often useful towards a much easier calculation of the electrostatic field when the system has some symmetry. This is facilitated by the choice of a suitable Gaussian surface. Only Gauss law is based on the inverse square dependence on distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law.